verbalizing the word problem.
Okay.
Trig.
Okay, go ahead. I'll try. Our audio is so poor that I'm not sure I can understand the word problem. You might be better off sending me a picture of it. But
you want me to try this first, or?
No, if it's not already written down, don't do that. Go ahead and try to describe it to me.
Alright, here, I'll try the first one. While hiking on a level path towards Colorado's Front Range, Odin determined that the angle of elevation to the top of Long's Peak is 30 degrees. Moving 1,000 feet closer to the mountain, Odin determined the angle of elevation is 35 degrees. How much higher is the top of Long's Peak than the elevation?
So the best thing to do on these trig problems is to draw pictures.
Yep.
Now, can you see what I've drawn? This is where you started, right here. The angle of elevation was 30 degrees to the top of the rocks. Well, as you started walking towards the rocks, obviously, as you get closer to the rocks, that angle of elevation goes up.
Yeah.
Okay. Now, they must give you some measurements here.
Yeah, it's 1,000 feet.
1,000 feet to the rocks?
1,000 feet from the 30 to the 35.
Ah, that's 1,000. Okay.
Yeah.
So this is 1,000.
Yeah.
Let's call that x, since it's unknown.
Okay.
Okay. Now let's call the height of the rocks h.
Okay.
So give me a trig function that relates x and h. Tangent of what?
30
equals
h over 1,025.
Now look at this triangle and give me another equation that relates x and h.
Tan of 35 equals h over x.
Now notice that I cannot solve either one of these by themselves. That's got two variables in it. You cannot solve an equation with two variables. But if you give me two equations with the same two variables, then I can solve it. This is just a number. Tangent of 30 and tangent of 35 is just a number. So it's not hard to solve for both h and x. It's two simultaneous equations. Let's do it if you don't know how to do it. You want to go through it? The solution?
Yeah.
Okay. So, on your calculator, what's tangent of 30?
Sorry, let me go run and grab my calculator. Let me go back there.
Okay, make sure you're in degrees. What's the tangent of 30?
And 0.577.
Can't understand what you're saying. What is it?
0.577.
Okay. Don't really need to say the leading zero. It's kind of worthless information, is it not?
Yeah.
I had this discussion with another student yesterday, and I tried to find out how come he always gave me that leading zero. It's a waste of breath. And I said, does your teacher do it that way? And he said, no, the teacher leaves it off. The teacher just says 0.577. There's no way you ever need to say that leading zero. That can be nothing but a zero. So it's like you don't say the 1 in front of the x. Just a point that it's not an important point. It's more of a curiosity on my part. Now, what's the tangent of 35 degrees?
0.7.
0.7?
Yeah.
Okay. Now notice what we have. We have two equations and two unknowns. Well, we know how to solve any system of equations that has two equations and two unknowns. How would I solve that?
Would you multiply the top one by 1,000?
Well, let's solve each one for h. That's probably the most logical way to do it. So the top one, h is equal to what?
1,000.
That, right?
Yeah.
Okay. The bottom one, what's h equal to?
0.7x.
And this is the same h. This h is exactly the same as that h. It's the height of the rocks. So now I can set that equal to this, and I'll only have one equation and one unknown. What's the next step in solving that?
Minus 0.577x.
Okay, so now I got 577 equals 0.123x, correct?
Yeah.
So now x equals 577 divided by 0.123, which is what?
4,691.
Now, that's x. Remember our original picture. They want the height of the rocks. So let's go into this equation, the simplest one. What's the height going to be?
I didn't know how to, I can solve it from there.
Well, once you solve for x, you still have to solve for h. And h is equal to 0.7 times x. So what's h equal to?
Well, you would do 1035 times...
No, you would do 4691 times 0.7. Remember, we solved for x. X was 4,691. Well, we have an equation that relates h to x. So multiply our x by 0.7 and you have your answer.
Yeah.
What is it?
3,282.7.
Didn't hear those last two digits, but we'll pretend that's it. Okay? So that's how you solve this problem, is by setting it up. The picture is the most important part. Look at my picture. This is 1,000 right there, and I made up that variable to x so that I could write my two equations. Once you have two different equations and only two variables, you know you're going to be able to solve it. It's not super easy, but certainly that's algebra, not trig. Okay?
Yeah.
And that's you know, trig has a lot of algebra in it. In other words, to solve a lot of these trig problems, you've got to use algebra. And that's exactly what we did. We solved a system of two equations with two variables. And that's all we did. And that we were able to solve for both h and x. So this distance here was actually 4,000 something, 216 I think. And then that h was 3,218 or something like that. But notice the beauty of this problem. This is my favorite trig problem of all. Why? Think of the value of this. Think you're in a wagon train approaching Denver in 1860. And you measure the elevation to Pikes Peak. It's 30-degree angle. And you don't even know how far you are from the mountains. You have no idea. You could be 100 miles, you could be 2 miles. But you go 1,000 feet and you measure the angle again, and now the angle says 35 degrees. And from those two measurements, you can calculate everything. The distance you are from the mountains and the height of the mountain. That is super cool. I mean, think about it. If you're in a wagon train approaching Denver 100 years ago and you see Pikes Peak, you have no idea how far you are from Denver, but using trig, you can calculate you're about 100 miles from Denver. That's when Pikes Peak becomes visible, is when you get about 100 miles east of Denver. But is all they have to do to figure out how far they are from Pikes Peak is to go another 1,000 feet and take another measurement. And that will tell them how far they are not only from the mountain range, but also it'll tell them how high the mountain is. Well, that'd be pretty valuable. If that mountain is 29,000 feet, then I'm not even going to think about crossing it. But if that mountain's only 14,000 feet, like Pikes Peak is, then maybe I can cross it with my wagon train. So this is a super cool problem in the fact that you can tell how tall a building or a mountain or a tree is by merely taking a couple of angle of incidence measurements. And they had that equipment. They had a surveying tool where when they were 100 miles from Denver, they could point it at the top of Pikes Peak and see that it made a 30-degree angle. So they had that equipment, even though they had no idea how far they were away. They just go any distance they want. Doesn't have to be 1,000 feet. It could be 500 feet. It could be 5 miles. Then take another reading. You get a 35-degree angle. It's all the information you need to know how far away from Pikes Peak you are and how high Pikes Peak is. Pretty cool.
Yeah, I got some more problems.
Okay, what else you got?
So the next one is the Coast Guard cutter and Joseph traveled at 30 knots from the town port on a course of 95 degrees for 2 hours, then changes to a course of 185 degrees for 2 hours.
All right.
And then find distance there from the port to the boat.
All right. When you give bearings in seafaring language, you're talking about angles from the north. In other words, the first direction of 95 degrees is not 95 degrees from the horizontal axis like we're used to. It's 95 degrees from the north axis. And I believe it's measured in a counterclockwise direction. In other words, that, clockwise, I'm sorry, not counterclockwise. There's your 95 degree angle, right?
Yeah.
Am I correct in that?
Yep.
Okay. And then we change directions to a 185 degree angle. Well, that is that. In other words, a 185 degree angle from north would be about what I've drawn.
Yeah.
With me?
And it happens to be a triangle.
Sorry, what?
And doesn't it happen to make a right triangle?
Well, I don't know yet. I have no idea. The only thing I know is that this is an accurate model of my picture, and if I label that as 30 knots, it's a vector, and then I got another vector, and I'm assuming we did not change speeds. We also are going 30 knots for 2 hours.
So aren't those all 16 knots?
How far do we go on the first bearing? If we're going 30 knots per hour for 2 hours.
60.
All right. The side of that triangle is 60. And the side of the other triangle is also 60, because we're still going 30 knots for 2 hours. So that's 60. So now is all you got to do is solve that triangle to figure out what x is. Now, what's this angle Z right there?
I think it's 90.
Yeah, in other words, you think correct. If that line is 95 and this is 185, then that's a 90 degree angle. Okay, so it is a right triangle, and the only thing we have to do is solve the right triangle. Well, let me draw it with a little different bearing or a little different perspective. We're trying to solve for x. That side is 60, that side is 60, and it's a right triangle. What is x? Use the Pythagorean Theorem, or else use your knowledge of 45-45 right triangles.
So it's the square root of 720, which is...
It's actually the square root. 60 squared is 3,600.
Oh, yeah.
So it's the square root of 7,200. Okay. So what is that number? What's the square root of 7,200?
84.85.
So that's how far away you are from your starting point. 84.85 knots. Now the question is, what is your bearing? In other words, your position not only requires a distance, but it requires a bearing. What is this angle right there? Actually, what is this angle? Because that's the way bearing is given. Let me write it in red. What is that angle right there?
Was 95 plus...
Good. What's this angle right there? It's a isosceles triangle. Got to be 45, right? In other words, this is a 45 degree angle and that's a 45 degree angle. Anytime you have an isosceles right triangle, the two acute angles are equal to one another, and they're both 45 degrees. So if that's 45, then the full angle is 95 plus 45. So this full angle is 140 degrees from north at a distance of 84.85 knots. That's where the boat ends up. Is as if, it's exactly the same as if the boat would have headed off on a bearing of 140 degrees and gone until it traveled a distance of 84.85 knots, it would end up right there.
Yeah.
Same place it ended up doing what it did. Just required a lot of math to figure it out because it took two different paths. But the secret to these problems is always to draw your picture properly.
Yeah.
Because only when you draw your picture can you see, oh, I'm looking at a right isosceles triangle. And once you decide that it's a right isosceles triangle, then that becomes the picture. And I know he went 60 total knots on the short side and 60 knots on the other short side. So I can figure out x using Pythagorean Theorem. And I can figure out the fact that that's got to be a 45 degree angle. So the total angle's got to be 95 plus 45. This is a relatively hard problem. I assume, I didn't hear it completely, but I assume what they were asking for was the position of the ship, right? How far away is it from where it started and at what bearing?
Yeah, that's 5 distance bearing.
Okay.
From where?
Well, we got it. 84.85 knots. Who knows what a knot is? Who cares? If he was going at 30 knots per hour and he drove for 2 hours, he went 60 knots. I don't know what a knot is. I don't care. I mean, I know it's related to nautical mile, and that's related to real miles, but I don't really care. I can give my answer that he is 84.85 knots away from his starting point. And then whatever a nautical mile converts to regular miles, you could convert it if you wanted to. But you wouldn't have to. You could leave it in nautical miles.
Yeah. I've got one more that's kind of similar to this. That was stuck in there.
Okay, we may or may not have time to do it. Go ahead, we'll get started. At least we can probably draw the picture.
Alright. A boat travels at a speed of 40 knots from Fort Lauderdale on a course of 65 degrees for 2 hours, and changes to a course of 155 degrees for 4 hours. And then,
Same speed, I'm assuming. Still 40 knots per hour.
Yeah.
Okay.
So.
Let's graph the first path. Well, 65 degrees. That's the angle from north. So that's this angle right here, I believe, is it not? No, it may be this angle here.
It's going up from the origin.
So it's the way I've labeled it now?
No, it's the 65 degrees would start at the origin and go diagonally.
Okay, that's probably a better way to do it, is to start always at the origin. Okay, so 65 degrees from north, which is that way?
Yeah.
Okay. And we're going 40 knots per hour for 2 hours, so how far did we travel?
80 knots.
80 knots to get to that point. Then we changed our bearing to 155 degrees. Well, 0 degrees would be straight up. So 155 degrees must be like that. In other words, that's 155 degrees. And we went for 4 hours. How far did we go?
160 knots.
Okay, and now we have a triangle. And to figure out the position of that point is all we have to do is solve the triangle. Okay. And again, they've made it relatively simple. They've made a 90-degree angle there. Okay, so now you have a right triangle. Let me draw my right triangle. Well, I got the 90-degree angle there. My short side is 80. My long side is 160. So all I got to do is solve for x, and that tells me how far away I am from my starting point. That's the square root of 160 squared plus 80 squared. That's what x is. And then the angle I want to figure out is that angle right there. Because now I can add that to 65 degrees and know the bearing, the complete bearing, right? So I want the angle opposite the 160. I want alpha right there. You see where I've labeled alpha? Down in the bottom, you see where I've labeled alpha? It's the angle opposite the 160 side. Matches this. There's the 160, there's the angle opposite it. Okay, now tell me what alpha is. If you can solve for alpha, then we have our bearing. It's going to be 65 degrees plus alpha. Well, how do I solve for alpha?
Inverse tangent of 160 over 80.
Which is inverse tangent of 2. What's that angle?
63.48.
So our new bearing, if you look at my picture, since 63 is the measurement of that triangle angle right there, then our bearing has to be 65 degrees plus 63 degrees, or 128 degrees 48, 128.48 degrees. That's this total angle from there to there.
Yeah. So, we added it to 65.
And that's the way all of these problems you're going to do, is you're going to end up with a triangle that you have to solve. Where, I mean, it's nice that they gave you right angles. That makes it a little easier to solve. But even if they did not, even if they gave you angles where this was not 90 degrees, you could still solve it. You've learned the law of sines, I presume.
Well, yeah, that's what I'm going to have you help me with tomorrow's law of sines, Mom.
Well, we'll do the law of sines tomorrow.
Alright.
Alright, Max. Have a good night. I'll talk to you tomorrow.
Alright, thank you.
You're welcome. Bye-bye.